It is dusk. After piling on the pounds, this humble polar bear has begun its enormous trek on an exclusive diet of seal blubber. We're on an amazing journey to discover the secrets of its walking hibernation, fat mobilization, and breakdown. During periods of starvation and stress, fatty acids are liberated into the circulation from triglyceride stores. Seizing the opportunity, albumin greedily carries up to 10 fatty acids to deposit them in skeletal muscle, liver, heart, and kidney before taking off again. Privileged with their own chauffeurs, these fatty acids venture into the cytosol through facilitated diffusion. From here, the urge to degrade these to produce energy takes place in the secret den of the mitochondrial matrix. Here lies the tribe of enzymes required for beta oxidation. But to first get from the far and deep waters of the cytosol to the mitochondria, the fatty acid requires a two-step process: activation and translocation. Fatty acyl-CoA synthetase is the chief enzyme for fatty acid activation. It robs ATP of AMP, entrusting it to the fatty acid to give rise to fatty acyl adenylate. Relentless, fatty acyl-CoA synthetase then thrusts itself upon coenzyme A, snatching its acyl group and forcing it to join with fatty acyl adenylate. The progeny of this unholy union is no other but the infamous fatty acyl-CoA. Now fatty acyl-CoA demands a carrier protein to traverse the sacred inner mitochondrial membrane. The always humble carnitine acyltransferase 1 comes to his aid and relieves its master of the acyl-CoA appendage for carnitine. The product of this traditional exchange is fatty acyl carnitine. Well equipped and fearless, fatty acyl carnitine readily crosses the inner mitochondrial membrane. Carnitine acyltransferase 2 swaps out the carnitine group back for the previously discarded acyl-CoA, creating the fatty acyl-CoA which nature has long sought after. Oxidation ensues in this mitochondrial matrix when fatty acyl-CoA encounters the ravenous acyl-CoA dehydrogenase. It tears off two unsuspecting hydrogen atoms near the CoA. A free hydrogen is paired to an accompanying FAD+ to give rise to FADH. Stripped of its hydrogen, this fatty acyl-CoA is now merely trans-delta-2 enyl-CoA. An enyl-CoA hydratase comes to its aid, providing some hydration. Trans-delta-2 enyl-CoA consumes H2O and transforms it into L-beta hydroxyacyl-CoA. But it's not over for beta-hydroxyl-CoA yet. Another predator, beta-hydroxyl-CoA dehydrogenase, attacks. It rips off the electrons and hydrogen off, leaving beta-ketoacyl-CoA behind. An NAD+ receives these electrons and H+, allowing it to mature into NADH, ready to start a new life in the electron transport chain. Beta-ketoacyl-CoA lies there in the dark abyss of the mitochondrial matrix. But all hope is not lost. Another enzyme, acetyl-CoA acetyltransferase, has picked up its scent. Escape is futile as it bears its sharp cofactor. The CoA-SH lodges in its backbone, separating two carbons in the form of acetyl-CoA. A leaner fatty acyl-CoA emerges from the aftermath, and the cycle renews. Here is another fatty acyl-CoA going through the steps of beta oxidation. But there is a problem. The double bond is in cis formation, so enyl-CoA hydratase cannot hydrate it. Luckily for our molecule, delta-3, delta-2 enyl-CoA isomerase remedies the situation, and our molecule can resume beta oxidation. But this victory comes at a cost. One less FADH2 is produced. The story would have been different if the double bond was even. There's no room for double bonds here, so 2,4-dienyl-CoA reductase reduces it to a single bond. 2,4-dienyl-CoA reductase cannot fulfill its destiny without the ultimate sacrifice of valuable electrons from NADPH.